When they say that planets are round, the reason is usually because gravity pulls everything toward the center. That answer is both correct and incomplete at the same time. It explains the direction of the force. It doesn't explain why this force overwhelmingly wins in one place and simply loses in another. The Earth, measured by satellite with centimeter precision, has bulges and depressions of up to 100 meters compared to the perfect sphere that gravity should have created. And orbiting the same sun, right now there are chunks of rock the size of an entire city shaped like potatoes, full of jagged edges, just as they've been for billions of years. If gravity alone were enough, these asteroids would have already become spheres. They didn't. If this force were relentless enough to decide on its own who becomes a perfect sphere and who stays crooked forever, what would it do with the exact opposite of a crooked asteroid? To see how far it can go, let's use an object that never really existed. A perfectly cubic planet the size of Earth. A cube of that size would have its vertices almost 4,000 kilometers farther from the center than the middle of each face, higher than any breathable layer of air. The corners would be outside the atmosphere, exposed to the vacuum, while the center of each face would still be within breathable air. Gravity there wouldn't be the same anywhere either. In the middle of each face, it would pull with almost the same force that you feel under your feet right now. At each vertex, it would drop to about 65% of that. A person standing right on the tip would weigh almost a third less and would feel the ground too slanted to stand upright. This planet would start to destroy itself the moment the last stone was put in place. Not because of a cataclysm from outside, but because of its own weight, pushing each vertex inward, slowly, until only one tip remained. Gravity doesn't know corners, but then the question comes back. If it's relentless enough to destroy an entire cube, why does it ignore an asteroid the size of a city, leaving it crooked for billions of years? Nothing in physics prevents matter from accumulating in any shape. Dust and gravel collide in space at random angles and form irregular clumps. That's how every planet starts, a shapeless heap, not much different from a common asteroid. The paradox is that this heap, if it grows big enough, forgets its original shape and turns into a sphere on its own, without wind, without water, without any frost at all. Mercury doesn't have an atmosphere to erode anything, and it's round. The moon has no rain or wind, and it's round. In these places with no wind, water, or frost, only one thing is left: weight. Mars has two moons, Phobos and Deimos, discovered in 1877 by the astronomer Asaph Hall. Phobos measures about 27 by 22 by 18 kilometers. Deimos, even smaller, measures 15 by 12 by 11. Neither of them is round. They're potato-shaped rocks covered in craters, orbiting a planet that actually is round. The difference between the moons and the planet they orbit isn't composition, distance from the sun, or age. It's just mass. The most common answer people give when asked is rotation. The planet spins, and spinning makes it round, just like a ball of dough spins in your hand and turns into a ball. It's the opposite of what rotation does. Rotation doesn't create roundness. It distorts the roundness that already exists, flattens the poles, bulges the equator, and never makes it rounder than it already was. Mercury hardly rotates, and yet it's practically a perfect sphere. The second answer is erosion. Wind and water wearing down the edges, like a river rounding a stone. But, as we've seen, Mercury and the moon don't have any of that, and they're just as round. I purposely disagree with how this is usually explained in short educational videos, as if erosion and gravity work together. They don't. Erosion polishes the surface. What moves cubic kilometers of rock from one side of the planet to the other is just the weight pulling inward. The third answer is chance. Matter spreading out equally in all directions purely by chance. It doesn't hold up to the numbers. If it were chance, there would be big, misshapen planets, just like there are big, misshapen asteroids. There isn't any. The transition from irregular to round always happens near the same radius. And that radius only changes depending on the material, ice or rock. That doesn't seem like a coincidence. It seems like a law. What really happens is that gravity pulls every gram of the body toward its center of mass by the shortest path. In a perfectly spherical body, that direction is always straight. But as soon as there's a bulge, a mountain, a corner, the material at that point is farther from the center than the material around it. And the force pulling that excess doesn't just point downward. It points a bit to the side, toward the center of mass, which is now shifted from the vertical at that point. That lateral component is the key. It pushes the bulge to the sides. And rock, under enough weight for enough time, stops behaving like a solid and starts behaving like an extremely thick liquid, flowing so slowly that no one can see the movement. But over millions of years, it redistributes itself until every point on the surface is the same distance from the center. That uniform distance has a name in geometry. It's called a sphere. To get a sense of this, think of a glacier. Solid ice, hard enough to walk on. And yet, it's still flowing down the mountain, centimeter by centimeter, every day. Rock, under the weight of the planet, does the same thing, only on a timescale so much slower that it's impossible to feel. But not impossible to measure. Physicists from the University of Adelaide calculated in a 2012 paper what would happen with water and air on a cubic planet like this. Since gravity pulls toward the center of mass and not perpendicular to each face, water and atmosphere would accumulate in the 6 lowest points, right in the middle of each face, leaving the edges and vertices dry, too high, exposed to the vacuum. 6 pools of ocean isolated from each other, each face evolving on its own until gravity itself causes the edges to flow downward and reconnect everything. That would start to happen almost instantly, geologically speaking. The cube would lose its very definition until you couldn't even call it a cube anymore. Feynman, in the early 60s teaching basic physics to Caltech freshmen, paused his reasoning on an almost trivial sentence. Everybody knows that the Earth is round. To ask why. The answer fits in one line. Everything pulls everything. And the body ends up attracting itself inward as far as it can go. And he went further. He showed that it's possible to deduce the Earth's exact elliptical shape just from the law of gravitation, without measuring anything. Flattened at the poles, bulging at the equator, because rotation slightly opposes gravity near the equator. Mathematics gives the answer before measurement confirms it. But the story has a twist. The asteroid Vesta, in the main belt between Mars and Jupiter, measures about 570 kilometers across its widest axis, almost twice the radius that separates a misshapen body from a round body. By the calculations, it should have already turned into a sphere. It didn't. NASA's Dawn probe entered orbit around it in 2011 and photographed an oval-shaped surface with more than 120 kilometers between its widest and narrowest diameters. The explanation is almost as interesting as the rule it breaks. A colossal impact in the past tore an entire slice off the southern hemisphere of Vesta. Gravity had already rounded the body. The collision undid part of the work, and there wasn't enough weight or time left for the rock to flow back. Vesta is a visible scar from a violent encounter, billions of years before any human existed to witness it. It doesn't weaken the rule. It shows that becoming a sphere is a process, not an instantaneous state, and it can be interrupted halfway. In 1687, Newton published the Principia with a testable prediction. If the Earth spins and is made of material capable of flowing, it shouldn't be a perfect sphere. It should be flattened at the poles and bulged at the equator. In France, the astronomer Jacques Cassini disagreed. His measurements pointed to the opposite, an Earth elongated at the poles. Two incompatible theories and no way to decide just by looking at maps of Europe. The difference was too small to show up in such a limited area. The French Academy of Sciences funded the solution to measure a degree of latitude in two very distant places, near the equator and near the pole, and compare the physical size of each degree in kilometers. If flattened, a degree would span more kilometers near the pole. If elongated, the opposite. In 1736, a group led by Maupertuis went to the Arctic Circle, carrying instruments over frozen rivers and in cold so intense it could crack metal. At the same time, Charles-Marie de la Condamine led an expedition to the Andes that lasted almost a decade, surrounded by disease and at one point, crime within his own team. Maupertuis returned in just over a year. The degree measured in the north was physically longer, a difference of hundreds of meters, small but measurable, and in the exact direction that Newton had predicted almost 50 years earlier, without ever leaving his desk. The Earth was flattened at the poles. Cassini was wrong. Voltaire coined the nickname that caught on in Paris. He called Maupertuis the flattener of the world, and Cassini at the same time. It was the first time that a human being measured, with an instrument in hand, physical proof that the shape of a planet follows a law, not an opinion, not an authority. The ruler confirmed Feynman even before Feynman was born. The same logic confirmed in the ice explains why a star that died thousands of light years away is also round. The asteroid Eros measures about 34 by 11 kilometers, more like a stone cucumber than a ball. And there is a physical limit to maintaining that. Most asteroids larger than 200 meters don't spin faster than one rotation every 2 hours and 20 minutes. Besides that, the force that throws the rock outward at the edges becomes stronger than the body's own gravity, which is too weak to hold the rocks together, and it starts to break apart. On the other end of the scale is Ceres, the largest object in the asteroid belt, round enough to have been reclassified in 2006 as a dwarf planet. It wasn't a bureaucratic whim. It was the recognition that there is a physical line separating bodies that gravity has already conquered from those it hasn't yet. Lynn Linweaver and Norman, Australian astronomers, published in 2010 where this line falls. Around 300 kilometers in radius for rock, 200 for ice, because ice yields to pressure much more easily. It was this line that removed Pluto from the list of planets. The discovery in 2005 of an icy object beyond Neptune, almost the same size, forced astronomers to decide what defines a planet. And the criterion included exactly this: enough mass for its own gravity to overcome the rigidity of the material and push it into a spherical shape. Pluto passes the test, but other icy objects out there also pass, and the decision to treat it as the prototype of a new category, not as the 9th planet, followed this criterion to the end. Jupiter and Saturn spin so fast, completing a rotation in just over 10 hours, that the difference between the equatorial and polar radius is visible even in a small telescope. The Sun, made only of gas and plasma, rotates much more slowly, taking about 27 days for one rotation. And the difference between its equatorial and polar radius is just over 6 kilometers in a body that's more than 1.4 million kilometers across. The Earth, rotating once every 24 hours, has a difference of 21 kilometers, making it proportionally much flatter than the Sun, even though it's 100 times smaller. Size alone never determines how much a body deviates from a perfect sphere. What determines it is the relationship between how much it spins and how much it weighs. At the very top is the neutron star. A teaspoon of its material would weigh as much as an entire mountain on Earth, with surface gravity about 1 billion times stronger than what you feel right now. Under that gravity, any irregularity is crushed almost instantly. The tallest mountain that could survive on the surface would measure, at best, a fraction of a millimeter. LIGO has already tested nearby neutron stars and hasn't found any with a deviation from a perfect sphere greater than 1 part in a million. The most extreme, densest, and most violent object that exists is also the most perfectly round. There's an irony much closer to you than any neutron star. A drop of water falling from a faucet also becomes an almost perfect sphere, not because of gravity, but because of surface tension pulling the molecules toward the center in the most efficient way physics knows. Two completely different causes, one governing entire planets, the other governing half a centimeter of water. They arrive at the same shape because the sphere is not the whim of either one. It's the shape that any free system chooses when all that's left is to save energy. That's why looking at the curved horizon at the end of an ordinary day is seeing firsthand the result of a process that began billions of years before any life existed on Earth. A shapeless mass that gravity itself smoothed out kilometer by kilometer until only this curve remained beneath your feet. You will never find an edge by walking straight across the planet. Not because the Earth is special, but because it had billions of years for the rock to forget every corner it ever had. It's impossible to say for sure how long a hypothetical cube would take to collapse back into a sphere. The actual speed of the collapse depends on details of the material that no one has tested at this scale. I'd rather admit this gap than make up a number that sounds precise but isn't. No rocky body larger than 300 kilometers in radius escapes this law. No ice body larger than 200 escapes, and no exception has stood the test of time without a specific explanation. Vesta needed a catastrophic collision to explain its irregular shape. It's the closest thing to a guarantee that physics usually offers. Gravity doesn't know corners. Given enough weight and time, it pushes every gram to the center until there's no corner left to hide. Going back to the cube, it would collapse. But why, exactly, does solid rock give way? The answer comes down to a number, and that number explains far more than just a hypothetical planet. It's worth making a side note before we continue. No cubic planet would ever actually form. Dust and debris colliding randomly would never produce a perfect geometric shape like this, only irregular clumps. The cube here isn't a prediction of how a planet could be born. It's an extreme example built on purpose because its symmetry makes the calculation exact. And it's this exactness that makes it absolutely clear, without any ambiguity, just how far gravity is willing to go. Every material has a limit to how much weight it can handle before it gives way. Engineers call this compressive strength. For granite, that limit is around 200 megapascals. If you stack rock high enough, the weight of the column itself at the base exceeds that limit. The rock stops behaving like a solid and starts to flow, and the mountain stops growing. Doing this calculation for Earth, the density of the rock, gravity here, the strength of granite, the result comes out to about 10 kilometers. And here's something interesting. Everest is 8,849 meters tall. It's not tall just because someone measured it that way. It's already close to the physical limit that any rocky mountain can have on this planet. And it keeps growing, very slowly, a few millimeters per year, pushed by the collision of plates toward that ceiling it will never be able to break through. There's a real demonstration happening right now of how deceptive solid can be. At the University of Queensland in Australia, a professor named Thomas Parnell poured melted pitch into a glass funnel in 1927. The pitch cooled and became hard enough to shatter if someone hit it with a hammer. But since then, it has been dripping, drop by drop, through the funnel. Only 9 drops have fallen in almost 100 years. And by an almost comical coincidence, no human has ever seen one fall in real time. Always during the moment when someone leaves the room or during a power outage right when the camera should be recording. The physicist who took care of the experiment for more than 5 decades died without ever witnessing a drop touch the bottom of the beaker. The pitch didn't know and didn't care that someone was waiting. In almost a century of the experiment, it never needed any extra force to push it. Only its own weight, along with enough time, was able to move a substance that looks like stone. Rock under the weight of a mountain or an entire planet does exactly the same thing as this pitch, only on a timescale so much longer that not even 100 human lifetimes stacked together would be enough to see the result up close. Now just change one variable, gravity. On Mars, it's 38% of the gravity here. The same rock, with the same strength, can stand much taller before giving way. Olympus Mons, the largest volcano in the solar system, is 21.3 kilometers tall. That's 2.5 Everests stacked on top of each other. It's not a better mountain. It's the same physics, just with weaker gravity pushing the ceiling farther away. That changes the scale of what would happen with a planetary cube. A vertex 4,000 kilometers high isn't a very big mountain. It would be born having to withstand a pressure that exceeds by orders of magnitude what any rock can handle anywhere in the known solar system. It wouldn't be a mountain range slowly rising until it stops on its own, the way any real mountain behaves. A vertex like that would be about 400 times higher than the maximum height any rocky mountain can have on this planet. It would be an almost instant collapse because the weight would already be far beyond the limit. Not geology, but fracture physics. You can feel the same logic with your own hands without leaving home. Pour dry sand to form a pile, and it never stays flat. It rises up to a certain angle, always about the same, and any grain that goes beyond this angle slides down until it settles again. This angle has a name, the angle of repose. It's the balance point between the weight of the grain wanting to go down and the friction holding it in place. A mountain of rock on a scale of billions of tons follows the same logic, except that the grain there is the entire mountain, and the friction is the resistance of the material itself. If the weight exceeds what this friction can handle, it slips. It's the same rule as the pile of sand, just written in kilometers and millions of years. And this logic, turned upside down, also explains why some bodies stay crooked forever. A small asteroid never accumulates enough mass for the stress from its own gravity to even come close to rock's limit. The bulge, the edge, the entire irregular shape, none of that receives enough pressure to flow. It remains frozen just the way the collision or the accumulation of dust left it. Not because the physics is different in these bodies, but because the physics never really gets tested. Before any probe photographed an asteroid up close, astronomers already knew that many of them were misshapen, without taking a single picture of their shape. The method is simple to describe. A spinning asteroid reflects more sunlight when it shows its wider side to Earth, and less light when it shows its narrower side. By measuring this brightness going up and down, cycle after cycle, it's possible to reconstruct how much its width varies, and with patience, even get an approximate shape without ever having actually seen the object. This type of light curve has been measured since the first half of the 20th century. The ruler, once again, got the right answer before photography even existed. The asteroid Cleopatra, in the main belt between Mars and Jupiter, is practically the limiting case here. It is 270 kilometers long, shaped like a dog bone, with two thick lobes connected by a thin neck. Suspected by radar for over 20 years and photographed in detail in 2021 by the Very Large Telescope in Chile. It is metallic, probably nickel and iron, but the measured density is too low for it to be a solid block of that metal, which suggests that inside it is also porous, a pile of poorly compacted debris, not a solid piece. And it spins so fast that the very astronomers who studied it call it critically rotating. It's close to the speed at which the centrifugal force would throw pieces of it into space on its own. Half impossible mountain, half ticking time bomb. And Cleopatra has two moons of its own, named Alex Helios and Cleo Selene. Many astronomers suspect that they formed exactly this way, material torn from the surface itself by rotation almost at the breaking point, which never fell back and ended up becoming a companion in orbit. Farther out, at the edge of the solar system, there's a contrast that's worth more than any example of violent collision. On the first day of January 2019, NASA's New Horizons probe flew by an icy object nicknamed Snowman at the time because of its shape, with two lobes stuck together. Unlike bodies that become misshapen due to violent impacts, this object, now called Arrokoth, kept this shape because the two lobes came together slowly in a collision so gentle that they practically embraced instead of destroying each other. It's the most distant object that a human spacecraft has ever visited up close. And because of that, it's one of the few places where you can still see, almost intact, the raw form that the building blocks of planets look like. 4.5 billion years ago, before anything collided with enough force to erase that memory. Its surface is reddish, almost the color of rust, a common shade in objects so far from the sun, caused by billions of years of cosmic radiation, slowly cooking simple organic compounds on the icy surface. It doesn't just preserve the original shape of the building blocks of the solar system. It also preserves, frozen in its very color, the chemistry that existed before any planet was fully formed. Many spinning top-shaped bodies seem to converge on the same shape for a very specific reason: sunlight. Photons hitting the surface of a small asteroid give it an almost imperceptible push, so weak that it only makes a difference after tens, sometimes hundreds of thousands of years. But with plenty of time, this push gradually speeds up the rotation of the body, slowly, until it gets close to the breaking point. And when that happens, the material closest to the equator, which is already being thrown outward by the rotation itself, starts to slip and accumulate in a ridge around the body's waist. It's the most widely accepted hypothesis today to explain why so many small, loose asteroids with different compositions end up converging to the same spinning top shape. There is still debate among scientists about whether this is the only possible path. Some bodies seem to have been born almost in this shape, without needing the solar push to get there. But the observed pattern, from metal to ice, is too widespread to be a coincidence. And then, there are cases that break even the intuition that crooked means solid, just badly formed. Bennu, visited by NASA's OSIRIS-REx probe, and Ryugu, visited by the Japanese Hayabusa 2 probe, Both have almost identical shapes. Toy top, with a wide ridge running along the equator. And both have such a low density, around 1.2 grams per cubic centimeter, almost the same as water itself, that it can only mean one thing. They're not solid rock at all. They're a loose pile of boulders and dust floating together, held together almost only by their own extremely weak gravity. The gravity on Bennu's surface is about 100,000 times weaker than it is here. And it spins so close to its own breaking point, it completes a rotation every 4 hours and a bit, and the probe recorded, on more than one occasion, boulders being ejected from the surface on their own, flying away and then coming back. An asteroid that literally spits out rocks from time to time. One of these spinning tops, called Didymos, became famous for a reason that has nothing to do with pure astronomy. In 2022, NASA deliberately crashed a spacecraft into its moon, Dimorphos, just to test if it was possible to actually push an asteroid in case one ever needed to be diverted from Earth. The collision worked. It changed Dimorphos's orbit around Didymos by about half an hour, more than expected. And the reason the test works so well is exactly what this whole video has been showing. Dimorphos is not a solid rock armored against impact. It's another loose pile of debris, just like Bennu and Ryugu. So the impact didn't bounce off. It pushed the whole body, like punching a pile of sand instead of a rock. It was the first real test of planetary defense in history. Not because Dimorphos threatened Earth, but because if one day a similar asteroid threatens us, now there's a real number, measured in space, of how much push it takes. And that number only makes sense because we now know that most of these bodies aren't solid rock. They're loose rubble, exactly the kind of target that gives way easily to a well-placed push. Noticing all this changes what shape means. It's not about the material being rock, ice, or metal. It's about a single ratio, how much gravity can squeeze, divided by how much the material resists. On a mountain, that ratio decides where the ceiling is. On an asteroid, it decides whether it will ever have enough weight to even test that ceiling. On a hypothetical cubic planet, it decides that it wouldn't even exist long enough to earn that name. It's the same calculation, done 3 times, on 3 completely different scales. And it always comes to the same answer. This whole balance, the point where the weight finally overcomes the resistance of the material and the body becomes a sphere, has a technical name: hydrostatic equilibrium. It's literally the official criterion that the International Astronomical Union uses to decide what is or isn't a planet. A 200-kilometer asteroid never gets there. A 10-kilometer mountain on Earth is already right at its threshold. And a planet-sized cube would be so far above that threshold that balance wouldn't even be the right word. It would just be collapse, measured in geological seconds. That, all at once, answers the 2 questions that open this video. Why do asteroids have strange shapes, but planets never do? Why does an asteroid never accumulate enough mass for its own gravity to overcome the resistance of the rock? Does it stop growing, or is it broken apart before that, always on the lower side of that line? And why does gravity prevent planets from being square? Because for a body to reach the size of a planet, it necessarily needs to cross that line. And on the other side of it, no shape survives except the sphere. There is no comfortable middle ground. Either the body is too small for the rule to apply, or it's too big to escape it. There is an even more extreme version of this rule, and it doesn't just decide the shape of the body, it decides whether it can exist intact. In 1948, the French astronomer Édouard Roche calculated, just on paper, the minimum distance at which a moon can orbit a planet, before the tidal force of the planet itself overcomes the gravity that holds the moon together. Get too close, and the side of the moon facing the planet is pulled with a noticeably greater force than the far side. And that difference, given enough time, stretches the body until it breaks apart. No one could confirm this by observing it up close at the time. The math came decades before any telescope could resolve enough detail to test it. And the test is literally hanging in the sky. Saturn's rings are almost entirely within this critical distance, a territory where, if all that dust and ice tried to come together into a single moon, Saturn's own tide would undo the work before gravity could finish assembling the body. It's not that the rings haven't become a moon yet, just waiting for the right moment. It's that, at that distance, becoming a moon is physically forbidden. Forever, not just for now. The Roche limit uses the same logic as this whole video, just inverted. Instead of deciding what shape a body has, it decides if there's any shape it can maintain. Every mountain you've ever seen in a photo, then, isn't a stationary monument. It's a temporary tie, the exact point where the weight hasn't won yet today. Everest is right now giving way, slowly, in the same way that the edge of a cubic planet would give way in seconds. The same law, only on a timescale generous enough to fit within an entire human life without anyone noticing the movement. You are also made of the same physics, only on the side that loses every day. The cells in your body are constantly pushing against that same gravity. That's why standing up is tiring. That's why astronauts lose bone mass in space, where that struggle simply disappears. You don't usually notice it, but you're exactly where a mountain is. Maintaining, for now, a stalemate that only exists because neither side has lost yet. And if there's a place where this fight is truly won, with no tie left over, it's the neutron star. A gravity so brutal that neither a human body, nor a mountain, nor even an entire cube would survive for even a second near it. Keep this question in mind. What would happen to anything, including you, near a neutron star, where not even rock, metal, or bone survives intact?